Okay, so welcome back. Obviously, we switched speakers, so our next speaker up is Sumit Kumar of Analog Devices in India, where he's a senior engineering manager on design verification. His talk is on AI and ML in semiconductor design verification, the next big disruption. He has over 15 years experience in AI-driven SoC verification. Having worked at Cadence and Broadcom, he specializes in pre-silicon and post-silicon validation, AI-powered verification, guiding large-scale SoC projects to be successful first-pass silicon. His extensive experience spans across pre-silicon verification, post-silicon validation, emulation, hardware, software, co-verification on complex multi-core systems. And he's based in India. Okay, over to you, please, Sumit.
Sumit, you can start your presentation.
Yeah, okay. Thanks, Mike. Thanks for the introduction. Good afternoon, everyone, for the audience and the people who are joining offline and online. Yeah, so it's pleasure to giving the heads up or the content on the AI and ML in the semiconductor in front of you. So it's I will start with my topic due to the time constraint directly onto the topic. So yeah, so now today the topic and the basically the problem statement which I will be covering is the complexity of SoCs in the has rapidly or they scaled rapidly, which increased IP and the heterogeneous compute blocks, CPU, GPUs, DSPs, and other things. So there are so much. I mean, the traditional verification limits. They have a certain limits. Whether it's a simulation or the formal based approaches, they struggle to keep pace or the coverage, debug speeds, and the lead bug detections. So through this presentation, what I am trying to cover is mostly we are trying to adapt the smart techniques that reduce human dependency for the pattern recognition and the debug, and also enabling the dynamic and the predictive verification workflow. So that is what I'm going to covering, and the real application is like practical use case of AI and ML in the verification, how it optimizes the test generation, whether it's coverage closure, debug automations, and the future prospects, like including the AI assistant tools and the methodologies and the challenges what we are going to face. Yeah. So these are the currently challenges which in summary which normally if a single core or multi-core or the SoC face with whether it's just a detailed breakdown, like whether it's when we talk about the increase in SoC and IP complexity, like the massive space due to many multi-core or the interconnect fabric is concerned. Verification of interconnect fabrics are very challenging in case of multi-core is concerned, and the protocol complexity, like we have AMBA, AXI, PCI, high speed DDRs grow with the chip scaling, and so these are causing a lot of the increase in the complexity of the SoCs. Again, the long cycle and the high cost. We have a time consuming simulations, regressions, high hardware emulation cost. Formal engine struggle to dig up with the or the catching the early bugs for the larger designs. Again, again also the scalability limitations we have, the legacy flow, whether it's a directed or the constrained random stimulus. So that sometimes we don't scale it linearly. We face a challenge in scaling up it linearly. Again, we are difficulty in achieving the coverage across the design configurations. And similar way, we have the other functional coverage gap, debug complexity, like we have a terabyte of waveform data, logs, assertions. So that basically cause lot of time as well as the resource in giving the DV closure or the making a certain decision making whether at what point of time our design verification is complete. the coverage closure becomes a bottleneck for any kind of tape out readiness. So through this, so these are the traditional verification challenges which we face across, and also the power performance is the trade-off. We have a difficult to model power assets, dynamic voltage scaling, or the traditional flow which ignores the workload realism. So all those things are the basic traditional verification approaches challenging, which I am trying to cover it up through my further presentations. So yeah, so coming now we are talking about everywhere about the AI and ML, the how we are trying to no change our verification process. So it's like how AI and address or the basically it's trying to cover the gap. So so from top level perceptions, whether it's machine learning which leverage the past regression data, or we can predict the test failure before simulation completeness, or we can identify the ineffective of the test cases early. No need to run the test cases which are not really effective or which are not actually giving any or catching any particular scenario, or it can be a redundant test cases. So those kind of in the when we have a huge database, there actually machine learning we can directly apply. Again, the for we can use the AI for the test generations also. We can reinforce the learning agents that optimize the test sequences for the coverage gain. Also, we can use certain kind of algorithm, which I will be explaining later, which train to focus the unexplored code paths, the whatever the code or whatever the design code which are unaccessed sites, we can target it first rather than doing the design reviews, design or the DV reviews, and then writing the test cases at the later end of the project. Or it may not be sometimes due to time constraint, we may not able to put that much effort while covering those holes, which is actually very important. Again, we have a NLP in verification, which basically automate, which it's a kind of automatic phrase natural language specs. Also, we have we can use certain ways to generate the assertions or the script to generate the assertion test plan, and basically reducing the manual misinterpretation. That is what we are more focusing on by using the AI and NML. So going to my next slide. So what are the techniques we can follow? So coming down, it's a short session, so I will be covering the top level, what all things actually we can use in the real time application. So first is the supervised learning. When we say supervised learning, that includes the input labeling, waveform, coverage, assertion data. We can label it and we can reuse for the future databases. Again, we can train the basically neutral networks to recognize the failure pattern, on what pattern the design is get failed. Those kind of learnings we can use it. Also, the application, like we can pre analysis, like mentioned earlier, we can catch early bug prediction. We can predict the bug within a certain pattern. We can use these logs, all the huge terabyte of logs, and we can try to analyze what is a particular pattern where the bug detection in a certain design, if we are reusing the certain designs, or we can reusing the IPs. So, and we can use the, by doing that, we can use the test effectiveness ranking also. So second thing is the that everything comes under the supervised learning, where we know, or we are able to supervise ourselves within a certain guidelines. Second is the which is not supervised, or it can be like which the simulation which are not labeled, or the cluster of data which detects the some wave off or some trade off which is present in the design. Or also it can be discovering the corner cases bugs and the misbehaviors that are not caught by the assertion. Generally we write based on our assumption how much we have understood the design. So these are the comes in the, we are just categorized what kind of AI and ML, basically categories or the techniques we can use. So these are the things which we can categorize as unsupervised learning. Then third is the reinforcement learning, as in the learning via the interaction with the duty or the agent which received the feedback or the coverage gain or the assertion hits, or the we can optimize the sequence in a constant random verification or the sequential sequences protocol. Those kind of we can gather the learning and we can come into the conclusion, like what certain patterns our which is a major area where we can we need to more focused on. So that will reduce the human in the time or the dv time consumption. The fourth one, which is the little bit it's a kind of, we call it NLP or the natural language processing. So generally we go through the design verification aspect, and we do the PRDs or the architecture documents on, and these will be the our case inputs, and the output will be, we generate auto generated system verilog assertions, checkers, or the test templates based on the spec. So these kind of scripting or the NLPs we can reuse. So this will certainly reduce the human what the error we do as a manual human error, and the improve the spec implementation, or also the traceability. We can able to trace what kind of on which particular spec and what are the checkers assertions, we can able to map it. So when we run the I think most of the places where we run the regression through vManager, we do the spec mapping. So it's more or less, we can at least we can save a certain amount of time, or the where manually tracing and the automated tracing, obviously we can reduce the human error while doing so. So these are the basic top level techniques we can categorize the ANI in the verification. So our coming to the next slide is the, these are the mostly real world applications. So I will give some 4 case studies, so which will tell how in real world all the real actual silicon or actual real case we can able to use this AI and the ML learnings in our verification flow. First is the basically AI powered test. So what we can do, we can optimize the test. We can use machine learning to identify the redundant test that offers no coverage at all, without doing all these running the regression first and then doing the analysis, and then through the tool we generate the coverage ranking, all those processes we follow. But so that pain we can avoid it. We can, by using these techniques, we can identify the tests which are redundant and which do not contribute to the coverage. Then we can, in the same, in the test optimization only, we can prioritize the tests which are very impactful and which reduces the simulation load. So we example, when we put the test cases in the GLS. So with this, we can prioritize rather the tool doing in or the manual process to do that. We can do it, and we can prioritize the tests which are more impactful, and which same way we can which test cases to rerun in the regression in point of seeds also. Suppose we want to rerun certain seeds or the certain test cases multiple times to cover the particular, or the test cases which covers the critical paths. So those way, in the power test cases optimization, we can prioritize the test cases which are more impactful. Second thing is the bug detection and the root cause analysis. So here what we generally do, we train the model, like based on the previous regressions or the result. We train the model in such a way to classify the localizations of the failure. Example, the timing failures or the protocol failures or the logical failures. So we train those patterns, like which can be whenever we have a new set of config or new set of data, at least we will be knowing okay, these failures are from this timing constraint or this protocol or this logic. So those kind of prediction we can perform. And also, like as discussed earlier, the basically we can use the NLP to summarize the long logs and highlight the whatever the root cause pathways. So whichever the path which is causing most of the bugs, we can obviously predict earlier and we can summarize the long logs. No need to rerun every time the same long running test cases. Again, the third is the basically AI assistant formal. So we can predict which assertion is likely to fail and which require manual intervention. So basically, we are categorizing where or which area of the uh, um, test bench, or whether it's formal or functional, mostly where we need more of manual effort, and we can rely most of the time in the assertions which has been already generated by the tool. So this will save a lot of huge amount of time. Also, we can use the AI to guide the assumptions, or to generate some bounding estimates. So that can be also this kind of estimations we can use through the formal engines. Again, in the post silicon validation, since I cover a lot of things in the post silicon, also in my real time scenarios, there what I see, we detect the real time failures. Example, few of the sensors or the registered traces. So there I see we can detect it early rather than doing a manual through the I mean, like manual running the post silicon test cases and then debugging it. So those kind of traceability, at least I can perform in my real time post silicon validation. Again, for the last case, like example for AI, we can do when we do the silicon bring up or the debug or the failure classifications. There also I can use this AI at least to predict, and that will save me a lot of time. And most of the times, what in the real world I am saying is, it's whatever we are getting from my predicted result, it's more or less closer to the directly jumping into the post silicon debugging. So whatever the area is pointing out, it's very close, and it saves me a lot of time. So now coming down to the more of a detail what actually it does. So example, I will just give a little bit more of a, because this is very critical what I feel in the real world, like how we can do the powered optimization test cases. So I think these are a few key points which this is a study, like case study, like these are the problems which we face generally. Like example, if we do what are the problems we can cover. So these are the few cases which I try to cover through these techniques. Like example, when we do the simulations, so at least we can target those areas, and that will save lot of simulations. I guess at least 30 to 40 or 50% I can able to save my simulation time. So that is also good amount, whether we do pre-validation or the post-validation. And again, we can retain the same functional coverage, code coverage for almost the number of test cases. We can the number of test cases which targets those amount of functional coverage, it reduces to a certain number, so that saves a lot of simulation time again. So we can have a certain categories of test cases or highlighted, or we can, it's a kind of more of a ranking which we predict the ranking of the test cases that covers most of the basically the functional coverage and the code coverage which we have coded in our test bench. So this is one of the example. And again, second, we like bug prediction, which mentioned the trained waveform, or the basically the we do a coverage profiling, and then we predict the failing runs. So based on that profiling, at least through the logs, we can collect the input data from the log, or from the failures, and then we predict the pattern, and we can reuse in subsequent releases. So where we see, like as I mentioned, there is a timing failure or certain protocol violations, or some few of the scenarios, few of the FSM's deadlocks. So that also we can predict very early rather than doing running the significant amount of test cases. Again, also that enables again automated assigning of the debug ownership also. What I feel is that, okay, if we predict which area or which reason the failure is mostly likely to be, I can easily appoint the person or the folk who is owning that block. So in that way, it's not only doing the technical help, it's helping me in resource optimization as a manpower also. We can able to save lot, we can able to plan my, if suppose we are doing on multiple projects, so it helps us planning the multiple resources also, whether which area or which part of the block is gonna have a issue, and we can appoint, or we can have based on the, we can make the decision making becomes quite easy. That's what I in the, so these all are the scenarios which I am telling is mostly the real time which I am facing in, and which I am using it in my pre and post silicon validation. Again, this is what I have just explained in a short while explaining the topic, that the formal where the basically where the things are not supervised, that these all the comes in the category which we don't supervise, or we don't have a certain set of data which pinpoint all these issues. So these comes in the category of unsupervised learning, where the formal engineers can focus and they can highly which are the basically basically the control paths or the logical paths directly. So instead of they going to, suppose a new folk who is going through the design and who is not aware of the past design works or the DV works, he faced lot of challenges. So this comes in the very segregated manner, and it's without any supervision. This the data which I get from the while doing the formal verification, and I can directly pinpoint the signals history, which are the historical failures and the correlations. So that improves my proof of the convergence, and it helps me in meaningful, basically a kind of assertion, fast doing the fast bug hunting also. If my resource also changes, it's keep helping me in doing the fast bug analysis and the assertion analysis. Again, in the post silicon, these are the details, few of the scenarios, like what are the basically in the silicon traces, or in case of the bug, and which are not reproduced in the simulation, that this causes, or this interaction, or the timing cases, or the finding these like corner cases in the post silicon, this is what I am getting help most of the cases. So which are not, which I am not able to reproduce in my simulation, actual simulation. So these kind of things, I just give a few of the examples which I have found it, which enables the early bug detection or the test reduction and the predictive insights in both pre and post silicon. So what are the framework basically we can work about? So when we say the framework, it's about, if we generalize the AI integration in DV, what it can be. First is the data collection. So second is the feature engineering, like where we give the exact relevant metrics, toggle rates, delay patterns, violation, what are the violation densities. Then third is the model training. We use the historical results and to train the predictive model. Once we design the model, or we create some AI model based on the reference historical results, so based on that we can able to predict the through the we can actually, so instead of documenting and giving the hands-on to the engineer wise, at least now we are training the model itself. Whenever some new folks run that model, we can able to predict the based on the past history logs. Now the third part is the deployment. So what after the once we integrate the model into the regression infrastructure, we do the real time automation, where actually the basically the whatever the we get the regression result through the uh, when we do the normal regression or the uh, regression, basically a kind of it's when we actually through the regression model we are trying to deploy the past history plus automation, as in simple words, when we say we are trying to reduce the long regression, number of test cases up to a certain level. When we club all the learnings, model plus feature engineering plus the data collection, which can be through waveform or through logs or the coverage or through the assertions. So yeah, so now what can be the future challenges when so I just first during the context which I told, it's what are the challenges we face in the traditional, and what are the four different categories or the ways which we can use the AI and ML in the both pre and the post validation, including formal, and then what are the future challenges can be. So it can be that we need to explain the AI to ensure we have a trust. Actually, that it should be trust in the decision, whatever the decision, or we can able to explain ourselves and the AI that whatever the decision we are gonna get, it should be the trustworthy decision. It should not be the data which we should feed the AI or through the model history. It should not be that it's gives some very unrealistic results. So that will be a challenge, and that will be challenge every time whenever there is AI and ML is used across any industry. So we have to, that trust factor will be always there. Again, the scalability. Now challenges in applying ML into the 100 million or 1000 million gates of SoC or multi-core platform will always be a challenge, because you until we never know what kind of output or how much we can able to scale it. So it's still these things are still in progress. We are scaling certain blocks, certain IP within the SoC. We are not scaling the entire multi-core SoC. The SoCs which are having 7-8 cores, still that trade-off is there. Again, the integration of legacy. Again, we have a legacy flow like tool chain, methodology alignment, all those things like simulator, VVM waveform, VVM framework, always a challenge, and verification in actual accelerators, which do not guarantee formal, where the formal are not guaranteed. So those are still a challenge. So coming down to, yeah, so these are the opportunities which is like we are yet to do the analysis, and we are actually we can explore more on it in the formal, in the verification flow, AI, hybrid, traditional, or the hybrid SOCs or the hybrid SoCs, and the predictive testing. Yeah, so these are the summary which I want to close on the topic, mostly on the, it's a vast topic, but I try to summarize within the 30-minute slot. So what all the basically how it disturbing the no, how it is basically disturbing the normal traditional verification methodology and the automation intelligence, how what are the challenges we are facing, and how to continue the doing the hybrid model. Yeah, and if any Q&A, please feel to mail me, or this is, yeah, this is my mail ID and this is my LinkedIn ID. Yeah, I think still I have one. I can take certain question if need.
Okay, so yeah, well, thank you very much. I think we're out of time, Sumit. But if we get any questions, we'll share them with you. Okay. Okay.
Sure,
Thank you very much.
sure, sir. Thank you so much, Mike.
Thank you.
Thank you.